Boldly going where no science show has gone before. The Naked Scientists.
Hello and welcome to the Naked Scientist Christmas special with Helen Scales.
Hello.
Dave Ansell.
Hello.
And me, Ben Valsler. Today we're looking at some of the seasonal science of Christmas. We will be finding out how churches get the best out of a choir and how we can indulge in a spot of acoustic archaeology to find out what a church might sound like long after the building itself is actually gone.
And in Kitchen Science, we'll be giving you the chance to meet your meat by showing you the anatomy of a Christmas dinner. Got a roast chicken ready, so we'll be showing you things to look for when you're carving up your Christmas lunch.
Plus, we hear about a breakthrough in cancer genetics. We'll be getting to grips with the evolution of those adorable, cuddly koalas. We'll catch an underwater volcano erupting, and we'll hear about a planet that's got enormous but very, very hot oceans. And of course, we'll be taking your science questions and answering our question of the week.
Hello, this is Alvin Raj from Cambridge, Massachusetts. Why is chocolate poisonous for dogs?
That's all to come on today's Naked Scientist, so if you want to get in touch with any questions or comments, we would love to hear from you. Our email address is chris@thenakedscientists.com, or you can find us on Twitter @NakedScientists.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
But let's start off with a little bit of science news. Now, the first comprehensive analyses of cancer genomes have been published in the journal Nature this week. The research, led by teams at the Wellcome Trust Sanger Institute, has been called truly groundbreaking by people at Cancer Research UK. What's so exciting about this work is not just that they catalogue the mutations in each tumour, but that their technique enables them to work out the causes and the history of the mutations. Looking at two patients, one with lung cancer and the other with melanoma, Mike Stratton and colleagues sequenced both tumour cells and healthy cells, and they could then compare like with like to identify which parts of the DNA differed in the cancerous cells. By doing this, they discovered over 23,000 mutations in lung cancer and in excess of 33,000 for the melanoma. We've known for a while that these two cancers have very strong associations, with tobacco smoke for lung cancer and with exposure to UV radiation in melanoma. Looking at these mutations and the genes around them, the researchers were able to identify a mutation signature for each risk factor. For example, many of the mutations relate to chemicals in tobacco smoke that bind to and interact with DNA. With melanoma, Dr. Andrew Futrell from the Wellcome Trust Sanger Institute said, "We can see sunlight signature writ large in the genome." I thought he put it so nicely that I'd use his own words. They also found telltale signs of attempted but failed DNA repair, which suggests that our bodies try and often fail to repair the damage done. This work further shows that there isn't a single triggering factor for cancer. The mutations build up over time and exposure, spanning years before the cancer itself becomes apparent. Which of these mutations are responsible for making a cell cancerous is now the major challenge for the next few years. Other cancers have far less obvious risk factors, and sequencing genomes is neither quick nor cheap, so there's still a great deal of work to be done. But research like this, combined with the fact that sequencing is becoming ever cheaper, will help to change the landscape of cancer research, prevention and treatment. So I think this is a very good story. Helen, what have you got?
Right, well, news this week that for the first time scientists have caught on camera an erupting underwater volcano. It's really very exciting. This is spectacular footage, and it shows enormous glowing bubbles of lava about a metre across, bursting into the Pacific Ocean, and for the first time lava flowing across the sea floor. And this is all about a kilometre below the surface, a bit more than that. And it's a type of volcanic eruption called a bonanite eruption, and it's only been seen before in extinct million-year-old volcanoes. This is really very exciting. This is the West Mata volcano, and it was visited by an unmanned submersible vessel called Jason, and that's from the Woods Hole Oceanographic Institute. And it's actually part of a huge major research project involving a group of researchers from all the way across the United States. And the volcanic explosions that the submersible was filming are in fact fact suppressed by the enormous pressure so deep down underwater. So what this means is that it allows the vessel to get extremely close to the erupting volcano, in fact up to just a few feet away, and that's much, much closer than on land or in shallower water. And there's an awful lot we can learn from this underwater volcano. The detailed footage and the samples collected by Jason will help to reveal many of the secrets of how the ocean islands are formed and how underwater volcanoes are born themselves, and just what's going on at a tectonic plate that's being subducted under another one, which is where this volcano was in the Pacific. And it'll show us things like how heat and carbon dioxide and sulphur are cycled between the deep interior of the Earth and the surface. And this is all very important because it's thought that up to 80% of the eruptive activity on the Earth actually takes place in the oceans, and most of it, like this one, are in the deep sea, and that's something that we really know very little about. Now, surrounding this volcano, and this is, I think, the most brilliant part of it, is some of the harshest conditions on Earth, and yet life has been found to be thriving there. Researchers have found a diverse community of microbes living around the volcano, and that's despite this huge, immense pressure and very acidic waters directly above the volcano because of everything that's spewing out of it. It's extremely acidic, it's about as strong as a battery acid or even stomach acid, and they've also found some shrimp thriving around these volcanic vents, and they've taken DNA samples by grabbing bits on the outside of Jason, and they're going to take them away and see how closely related these shrimps are to other submarine volcanoes. So this is telling us about this life that we really have very little idea about, but it's clinging on in the most unlikely circumstances, and it just really goes to show that we don't know so much about the Earth and how it works yet, and reminds us of what extraordinary things there are still waiting to be discovered.
It's astounding how little we know about the deep sea.
It is, but then if we think about it, it's quite a challenging environment to work in, extremely challenging, and it's just really exciting that we're getting down there and producing pictures of these underwater volcanoes. You wouldn't have thought such a thing was possible, but it's, in fact, masses and masses of volcanic activity that's going on, and it's really important, so it's fantastic.
It's not a very exciting name for a submersible, though, is it? Just calling it Jason.
Jason, I think it's quite sweet. But you're right, no, it's not very... Yes, anyway.
Thanks, Helen. Now, over the last few years, astronomers have discovered over 400 planets outside of our solar system. So far, most of these have been large gas giant planets, a bit like Jupiter or Uranus in our solar system, and most of them have been very close to their stars. Not because there's necessarily more of this type of planet in the universe, because they're much easier to detect. But now the instruments are getting good enough to detect smaller planets called super-Earths, which are sort of between a gas giant size and the Earth size. There's two main ways of detecting these distant planets, either by looking at how their gravity moves their star around, and you can actually detect that by looking at light coming from the star, or by looking for the dip of brightness produced by a planet moving past its star. From the first, you can tell the mass of a planet, and from the second, you can tell how large it is, sort of its area. The bigger planets block more light. Now, using both of these methods, a group led by David Charbonnet from Harvard University has discovered a planet called GJ 1214b, orbiting a red dwarf star, which seems to have a mass about 6.6 times that of Earth, but a volume over 19 times larger, which means it has a density of only about 1.9 times that of water. Now, this could possibly be a very small planet with an enormous atmosphere, so it's blocking lots of light, but which is thought to be quite unlikely. Or it could be a small rocky planet surrounded by an enormously deep ocean, thousands of kilometres deep, which is a rather wonderful thought, a huge ocean like that.
Absolutely, yeah. And it's that deep. I mean, because we're on average about 7 kilometres, aren't we? So
yeah, I mean, the ocean on Earth is only a very thin layer over the surface. However, it might not be the kind of wonderful kind of place to go for your holidays and do lots of swimming, because it should be about 190 degrees Celsius on the surface, so it could be a bit warm.
Oh dear, okay. So I shall stay clear of that one, perhaps.
And they're not quite sure which one it is, but they're planning to use a Hubble Space Telescope to look at the light coming from the planet directly and spectroscopically try and work out what it's made of and if it is actually got lots and lots of water in it.
I wonder if anything lives in it as well. I mean, it could do, couldn't it? It'd be exciting.
It's always interesting to think that there might be planets out there with things that we've never discovered living on. That's definitely something for the future, though, unfortunately. Now, the way that we remember dance moves reveals the incredible flexibility of the human brain, according to research published in Current Biology this week. Daniel Holm of the Max Planck Research Group for Comparative Cognitive Anthropology studied the way that different cultures remember dance moves, and this was inspired by previous research that shows how different cultures use different strategies for describing the world. For example, I might think that the microphone on this desk is in front of me, whereas a nomadic hunter-gatherer from Namibia, if he were in the studio next to me, would think of the microphone as being to the west of him. These are two different ways of encoding the spatial relationships between objects, and they're called egocentric, which is based around yourself, and allocentric, effectively based around everything else. And our brains use these two interchangeably. However, the way that the brain encodes the positions of our hands and our feet, this is called proprioceptive space, is strongly egocentric, so it's always based around us. Now, because of this, you might assume that the way we move our bodies would also be egocentric. We would always base these movements around ourselves. However, it seems that that's not always the case. The team asked two groups of children to learn a simple dance, one group from Germany and another group of San or Bushmen called Haikom. The dance instructor stood next to the children and showed them a simple dance sequence that involved shaking clasped hands together from side to side, starting with the right, then the left, and then back to the right. So once the children had learned the dance, they were asked to turn around, so they were facing the opposite direction, and do the dance again. The German school children almost always moved their hands to the right first, regardless of what direction they were facing. The Haikom children, however, would switch movements depending on which way they were facing. The direction was absolute rather than personal. So if they started on the right when they were facing north, they would start on the left when they were facing south. Now, this shows that the way our brain codes our body movements is not strictly egocentric, but it is in part defined by our culture, or as they put it on the paper, cultural diversity goes hand in hand with cognitive diversity. This may sound like a bit of fun, but it does have a serious message about the way that we study the brain. When we seek to understand cognitive function, it's vitally important to include a cross-cultural perspective. The brain does not exist in isolation. Horn said it's becoming more and more clear that we cannot simply extrapolate from investigations within our population to others. To understand the human mind, we need to widen our perspective and assume diversity rather than universality of cognition until proven otherwise. So there you go. If you're studying the brain, bear that in mind.
I think that's definitely something to bear in mind if you're on the Christmas dance floor. And maybe it's an excuse for some of the poor shows on the British dance floors. I'm always convinced that, you know, compared to other cultures, the Brits aren't good at dancing, so maybe it's something to do with our brains. And the way we're brought up, who knows?
Who knows?
Anyway, I'm going to move things a bit further south now to Australia and those dozy, lovable emblems of Australia, the Australian outback, if you like, the koalas, and they look like teddy bears. But being marsupials, they're only very distantly related to real bears. And a new study sheds light on the little-known evolution of koalas, revealing that their ancestors didn't have the specialised teeth and jaws that would have allowed them to eat tough and somewhat toxic eucalyptus leaves. And it turns out that koalas were actually only more recently adapted to cope with this unique diet. Now, publishing in the Journal of Vertebrate Paleontology, researchers from the University of New South Wales and CSIRO in Australia investigated the fossilised skulls of two koala species that lived once a long time ago in Australia in the Miocene. That's around 24 to 5 million years ago. Now, the team also found some striking similarities in these prehistoric and modern koalas. Both of them have a round, hollow, bony structure in the ear, which is a key to their ability to create loud and complex vocalisations. Because koalas may be lazy, but they can be extremely noisy, bellowing at each other across the treetops. And it's something, it turns out, that they've been doing for quite a long time, and long before they evolved their eucalyptus leaf habit. Now, the eucalyptus has really only became abundant as Australia drifted away from the tropics, and it became drier, and there were less rainforests around. So that kind of makes sense that they adapted their diet to deal with these different trees. But that's not the only news we had this week about koalas. Rather sadly, we also heard that they are among a group of species that have been listed as the most likely to be hit hardest by climate change. Scientists from the International Union for the Conservation of Nature, IUCN, have highlighted the plight of a long list of species that will probably not fare very well at all in the coming years. And that includes clownfish, beluga whales, emperor penguins and all sorts of other things. But the koalas in particular may face starvation because the nutritional quality of the eucalyptus leaves that they love to eat so much is predicted to decline as levels of carbon dioxide increase. So there we go. We learned a bit more about koalas this week, but we also think that maybe their future is a little bit uncertain, which is very sad indeed, I think.
It is. I would have thought that eucalyptus doesn't have a great deal of nutritional value in the first place.
Well, exactly. And that is one of the sort of conundrums about koalas as to why they bother, because they aren't much fun and they supposedly make their brains a bit fuzzy too because of the eucalyptus oils in the leaves. But so they're really on a knife edge as it is. And if they lose that nutrition, it could be even worse for them. So
certainly something to keep an eye on, yes. Also in the news this week, scientists at Queen Mary University of London have discovered some fundamental differences between the bone in our skulls and the bones in our limbs, and this could hold the key to tackling bone weakness and fractures and osteoporosis. They've published their work in the journal PLOS One, and we're joined by Dr. Ian McKay to explain a bit more. Hi Ian, thanks for joining us.
Hello.
So what does happen to bones over time?
Well, there's a gradual and progressive loss of most bone structure and strength, and that will ultimately lead to osteoporosis.
And by osteoporosis, of course, it comes from bone and pores or holes, so essentially we're thinking of holes in the bones.
That's right, and it's so common. I mean, about 50% of all women over 50 are going to suffer from this condition in some form.
So what is it that you've been looking at?
Well, in one sense, it sounds like the science of the patently obvious, because we've been comparing the bones from the skull to the arm. But when you consider osteoporosis, what's interesting is that the skull really doesn't show the same vulnerability to osteoporosis as the rest of the skeleton. What's more curious, on that basis, is that we know that you need mechanical forces to maintain most of your skeleton. If you don't walk about, your bones will dissolve and be less strong. But the same is not the case for the skull, which doesn't actually experience the same mechanical forces as your arms and legs. Probably the forces on your arms and legs are maybe 20 to 30 times higher. So it's interesting why the skull should be protected in this way.
So is it not just the case that bones become weaker, such as the limb bones, because of the different mechanical stresses?
Well, it is to a certain extent, and you can maintain that by exercise as you get older, but the skull really seems to be completely insensitive to that. And what we've been doing is looking at the genetic differences between the cells that make the bone in your skull and in your arm, and we find that they are indeed quite different.
So these are factors that occur in the womb, I assume. So the different genes are switched on. Some say, I'm going to make skull bone that will never end up with osteoporosis, and others say, I'm going to make arm bone, it'll be under lots of tension, and eventually it may become weak.
Well, yes. I mean, I think this just emphasises the complex nature. People look at a tissue like bone and they assume it's uniform over the whole body. But in fact, if you think about it, your arms and your legs actually all experience different forces and are designed to respond to those forces differently. And what we're looking at with the skull is a very dramatic difference between being very hard and protective in the absence of these normal mechanical stimuli.
And as these are genetic factors, do they only really kick in the womb? What happens when we damage our bones and we have to grow back new bone to knit old broken ones together?
There's two aspects to that. The first is that you obviously do, when you regenerate you regenerate bone of an appropriate character for the damaged tissue. But the other thing is that this mechanical responsiveness that the most of the skeleton seems to show is something which seems to be acquired during development before birth in the maternal environment. And there's increasing evidence that actually what happens before birth will determine your final mineral mass, your final bone density and strength when you're an adult. And obviously the more bone you have, the less likely you are to be affected by osteoporosis in later life.
And obviously this is something quite important for this time of year. It's very icy out there, certainly in Cambridge at the moment, and people will fall, and when your bones are weak, certainly in the elderly, you can do a lot of damage to yourself. Are we learning anything from your work that can help to prevent this or help to protect people from damaging their bones?
Well, clearly, if there was a way of tricking or making most of the skeleton feel that they were a bit more like the skull, then you'd be able to improve or maintain mineral density. But really, we're at a very early stage. I think it was a surprise to some people to show that these bone cells really are that different. I think a lot of people consider that they are fundamentally the same.
Well, it's fascinating stuff. Where should we go next? Where's the next step for you?
Well, I think the next important step is to find out when, during development, the mechanical responsiveness is being established. There's quite good evidence, as I said, that you can direct or correlate changes in the maternal blood chemistry with the bone density of children who are 8, 9 years old. But what we don't know is when, during pregnancy, that important set point is being established, and I think that's a key element if we wanted to intervene and maybe manipulate bone density. And these kind of the gene work we've done will identify some of the markers which I think will be important in that.
Fantastic. Well, thank you ever so much for joining us in. We'll have to leave it there. That was Dr. Ian Mackay from Queen Mary University of London on how they've found some key differences in between skull bones and limb bones, and that these may give us some clues to help prevent bone damage or, in fact, have stronger bones.
Laying the facts bare.
I say.
The Naked Scientists.
You're listening to The Naked Scientist with Helen Scales, Dave Ansell and me, Ben Valsler. And this week we have a very festive Naked Scientist show for you. We'll be finding out how churches shape the sound of singing and how you can predict what a choir would have sounded like in a church that's long since been demolished. Plus, we'll be dissecting a Christmas dinner so you can meet your meat. If you'd like to contact us through Twitter, it's @Naked Scientists, or you can send us a good old-fashioned email to chris@thenakedscientists.com. But first, this is the very last Naked Scientist show of 2009, so we thought we'd look back on a few of our favourite bits. It's been a great year. We've had some really interesting guests, been to some incredible places and done some fantastic experiments. But first, Helen, what's been some of your favourite bits?
Oh, well, there's so much to choose from. But I think something that stood out for me was when we had Dr. David Aldridge in the studio from Cambridge University. And he brought with him some creatures found in fresh waters around the world that really shouldn't be where we find them. So this was all about the science of invasive species. And he brought some critters for us to look at.
And we can have a listen to that now.
I've got a little menagerie of goodies here. I've got some zebra mussels. I've got a signal crayfish from North America, and I've got a Chinese mitten crab. They're beautiful, but unlike our native freshwater mussels, which just sit in the bottom of rivers with their foot digging into the mud, zebra mussels have a beard, a byssus thread, which is like the marine mussels that you eat. So zebra mussels are able to sit on solid surfaces, and they can attach to each other and sit in dense layers. So they can foul pipelines, drinking water supplies, cooling systems to power plants, irrigation systems, but also they sit on our native wildlife. And one of the things they really threaten, such as this specimen I've got in front of me, are our native mussels, which provide a really good substrate, and they choke them and cause them to die.
Yes, because that's a huge mussel you've got there, and I can hardly see it. It's kind of covered in smaller zebra mussels. That's incredible. And the crayfish you've got there, that looks quite tasty. Can we eat those?
We can, and that's the reason they were brought over here. The American signal crayfish was brought over in the 1970s as a commercial aquaculture food. The problem with these crayfish is that they can walk over land, so they escaped out of these little ponds they were put in, and they can move into the wider environment. So they are very good at sort of changing the ecosystem through feeding on the bottom-rooting plants, the macrophytes, and they dig burrows which can cause sort of destabilisation of the banks. But perhaps of greatest sort of immediate concern is that they carry a fungus, something called crayfish plague, which kills our native crayfish species, but these are pretty resistant. The American ones are pretty resistant to. So we've had, for instance, in the Cam in 2000, there was an outbreak of plague which wiped out native crayfish from about 20 kilometres of river.
That was Dr. David Aldridge telling us about some of the creatures that get into freshwater bodies and cause trouble where they shouldn't be. And we had a look at some of them in the studio, and that was quite fun. That was great.
It's very nice to have our own invasion of invasive species. It's not often people bring things into the studio.
I think we should do that more often. That's what we should do in 2010, is bring creatures into the radio studio. Is that all right? With everyone else?
Well, we do have a cooked chicken with us today, but I think that's a slightly different way of thinking about things. Now, speaking of species that we don't want around, there was also a lovely news story from earlier in the year about the love song of the mosquito. Now, if you listen very carefully to this, you can almost hear Dr. Cat just squirming in her seat.
Now have a listen to this. That is a male mosquito buzzing its wings at something like 600 hertz, 600 times a second. Have a listen to the female mosquito, and these are Aedes aegypti mosquitoes. Here we go. Now, I won't subject you to too much more because Dr. Cat has got her fingers in her ears. But that's at about 400 hertz. But if you do what two researchers at Cornell did, that's Lauren Cater and Ben Arthur, they put one of those mosquitoes tethered to a pin with a piece of superglue so they could keep it in one place, and they bring in a mosquito of the opposite sex and they record what happens to the wings of the two. Have a listen to this. Now, what's actually happening is that the two mosquitoes are adapting the beating frequency of their wings so that they harmonise.
Isn't that lovely? Mosquitoes singing in harmony. And I've never seen such a visceral reaction as Kat squirming in her seat with that. Fair enough, it's a horrible sound, the sound of mosquitoes. But thinking of something a bit more pleasant, we've had loads of great experiments in kitchen science. I remember at the start of the year we made some jelly to show how fruit enzymes can cut up proteins and stop the jelly from setting, although I think it may have just been an excuse to make lots and lots of jelly. But Dave, what else have you been enjoying this year?
All sorts of things this year, ranging from videoing popcorn popping, watching the way it's absolutely beautiful, the way it kind of unravels as it's a really strong pressure vessel. You get it really hot, the water inside boils, the pressure builds up and it breaks and it opens itself up almost all the way. And you get this it pops out the place. I got a few minor oil burns from that one, so probably not something you really ought to try at home. And there have been all sorts of lovely things which I keep bringing out at dinner parties as well. There was one which I found from a guy I met at the British Interactive Group. And you just have a nut on one end of a piece of string and a mug on the other end of a piece of string, hold it over a pencil, and just let go of the nut. And despite what you'd expect, every time, as long as you don't mess up too badly, the nut wraps itself around the pencil and it doesn't hit the ground. And I also had one which I actually got a proposal of marriage from my housemate, which my girlfriend wasn't entirely impressed with, which was getting a orange peel, especially good juicy orange peel, nice big thick orange peel, and squidging it next to a candle. And you get these huge sort of fireballs, maybe 5 or 6 inches across, and it's absolutely beautiful, especially in slow motion as well.
That's very cool. I like that one too, actually. But another one that sticks in my mind especially was when you soaked me in the studio. I thought that was rather mean, but it was great fun, and I think we've got a clip from that one coming up.
So if you spin that nice and quickly...
Do I let go of it, or do I hold on to it?
keep holding it and spin it nice and quickly.
In one direction?
In one direction.
Oh! Oh, I see, I see. I'm
That's
covered
why
in
Dave
water.
got you to hold it. Yeah.
That's the last time I offer to have a kitchen science. So what happened is the water flew out of the open ends of the straw. I'd have another go, but I think I might get the microphone wet.
Yeah, we should probably be a bit careful.
That was really good.
It was like a rather beautiful fountain for a moment there.
Well, clearly that tickled Dr. Chris. Dave, did you know that was going to happen?
I'm afraid that fairly simple physics made it pretty inevitable that was going to happen, Helen.
Ooh, I'm shaking my fist. Oh, well, anything in the name of the naked scientist, that's fine.
Of course. And we didn't get any microphones wet, not at all. We never do anything that could in any way harm any of the equipment in this studio. Wouldn't dream of it. Now, I've really enjoyed meeting some of the people I've interviewed this year. I spoke to the Science Minister, Lord Drayson, about why science is so important. But a bit more fun was talking to comedian Robin Ince about how science and comedy are very closely linked.
Well, in fact, there is a huge and accidental rational movement, basically. And I think after we put together the show 9 Lessons and Carols for Godless People, where on the science side, you had Simon Singh and Ben Goldacre and Richard Dawkins. There are various musicians, people like Jarvis Cocker and Darren Hayman, and then comedians, and all of them were doing something on the rational world. And you have people like Dara O'Brien, Chris Addison, Stuart Lee and Josie Long, and all of them are approaching things from a rational perspective, and especially Dara, who has a physics background, he's very excited about talking about science. And I think there is, perhaps, I don't know, but perhaps because TV isn't really pandering very much to intellectual programming. So I think there has been an accidental rational stroke scientific movement start in comedy.
And we've also been to some amazing places this year. Laura Soul climbed to Everest Base Camp and reported back on how her body reacted to the low levels of oxygen. It clearly wore her out somewhat.
It's good to sit down. I have a massive headache, and so do most people. I felt a bit sick on the way up, but I'm okay now. some people feel very sick. The view from here is absolutely amazing. You can see the Khumbu icefall, which is really beautiful with these huge, big, jagged peaks of ice. It's been very hard work to get up here, but I'd say that it was definitely worth the climb.
I think you can just about feel, can't you, just how exhausted she is. It's amazing. Well, I was a little bit envious, I have to say, of Mira's trip to South Africa this year, and when she got to meet some cheetahs. How lovely.
Okay, somewhere very nearby here is a cheetah on a curicule. There we go. See, over the side. It's actually feeding.
Oh my God, yeah. Uh-oh, it spotted us. Does that matter?
Oh, no. They're very relaxed. It's feeding, so it's got other things on its mind. And cheetah aren't animals that are dangerous or anything to humans.
So we've pulled up alongside this tree, and I can see the cheetah's body and its head, and its tail's wagging now. And it is just quite literally having a feast down there, munching away.
You can hear how excited she is by that little gasp of breath. I was really excited to hear that. It's also quite nice to know that cheetahs are quite a bit like my cats at home, in that once you give them some food, they don't care about anything else whatsoever.
Distilling the best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
You're listening to The Naked Scientists with Helen Scales, Dave Ansell and Ben Valsler. And if you'd like to contact us through Twitter, it's @NakedScientists, or you can always send us an email to chris@thenakedscientist.com.
Thank you, Helen. Now, as it's Christmas, there will be plenty of carol singing, either through groups knocking on your door or going to carol services in church. But why is it that some places make a choir sound good, while others can make them sound flat and lifeless? Now, have a listen to this. And we're joined by Malcolm Longair, who's taken St John's College Choir to Venice to explore the acoustics of architecture and even indulged in some acoustic archaeology. But what are we listening to here?
What we're listening to here is a magnificent performance of the Nescience Matter of Jean Mouton, performed by the Gentlemen of St John's in the Emiliani Chapel in Venice. I should explain that this whole project came out of my wife's work. She is Professor of Architectural History, and since she's been working on Venice for almost 40 years, she wanted to understand exactly how music worked in the great churches in Venice. So she was very fortunate to get a very substantial grant to study this, to characterise acoustically exactly what the buildings were like, to take the St John's Choir out to Venice, to try all the possible positions and the various combinations, and also to get the audience responses to what they were hearing. So my role in this was very much secondary. I was the person responsible for doing the acoustic and the scientific analysis of the data, which appears as an appendix to Deborah's book, which only came out just last week.
Well, I'm pleased to hear it. I think I saw a talk by your wife a little while ago, and it is fascinating stuff. But what is the relationship between architecture and acoustics?
Exactly. That's what it was about. Now, the reason that this project was so intriguing is that the Renaissance period was the time when new music was being written, which required a very detailed understanding of polyphony. So the split choirs, where you would want to hear 8 voices, or something like the Gabrieli 15-part motets, you had to have an acoustic which would enable those who paid the money for the music to actually hear the 15 parts of the 8 parts. So that's a great acoustic challenge. And the architects such as Palladio and Sansovino, they were attempting to take into account these requirements in the churches they were building at the same time. Now, the whole project went extremely well, but there was a big problem, which is when we tried to simulate what this sounded like, we were getting far too long reverberation times. So what I've been doing with Braxton Boren, an excellent student who has joined me from the United States. We're building virtual models of all the churches for which we've got acoustic data, and we're trying to reproduce the acoustic volumes virtually. And the idea is that once we've done that, then we can change the nature of the buildings. We can put in different roofs, we can put different hangings, different audiences, different clothes, everything, and see how we would get to the proper understanding of what it must have sounded like in the 16th century when this was being done. So it's an absolutely wonderfully great fun project.
You've brought some samples with you today, actually. Now, this first one, this is the real acoustics. This is what it generally sounds like. Where is this?
Yes, this is a most wonderful place in Venice, which if you get to Venice, you can go into the Ospedaleto. It's got the most wonderful acoustics. And this is the sopranos from the St. John's Choir singing from the organ gallery of the Ospedaleto and being recorded in the middle of the nave. It's quite a small volume, but it's a very simple shoebox-like shape.
So it certainly sounds lovely, but how do you go about analysing the actual acoustics in there? How do you find out why it sounds so good?
Well, this is great fun. What we did was to characterise acoustically using the most modern equipment, source and microphone positions, and we did many positions within each of the churches so that we've got all the acoustic parameters that we need, the waveforms coming from all of these. Once we got that, then Braxton has built a virtual model of the church, and then we run it through the most recent program, which is a program called Odeon, developed in Denmark, which enables you then, once you put all the materials on the walls, marble, Latin plaster and so forth, to get what the response looks like. And so once we've got that, we can check that we've got this now, the calibrated data for this existing church, and we can then try to get this sound, all the acoustic characteristics right. And we've done that just within the last 2 weeks. Once we've done that, then we can then put an anechoic recording of the choir through our Wiltshire church and see if we've got back to where we are.
So we have an anechoic recording of the choir here. Now, this is in a room that just cuts down all echo, isn't it?
That's correct. This is done in West Road in the Music and Science Centre that Ian Cross runs there, and we got the choir in there. They hated this. This was really terrible. They did not enjoy this experience at all, but you'll hear what the anechoic signal sounds like.
Well, they certainly sound very capable, but it does sound very flat.
It sounds very, very dry, right?
Yes.
So what we now do, we take that same signal and we put it through our virtual model of the Ospedaleto, and you can see what it sounds like.
So all of that beautiful reverb that really brings that music to life is all fake, it's all simulated.
Well, depends what is real, what is simulated. That's right. Let me explain why we're doing this. The reason for doing this is this was the simplest example that we could get, and we wanted to find out the rules we had to follow to be able to do accurate reconstructions of the huge churches in Venice, things like San Marco, the Redentore, San Giorgio Maggiore, which we will now begin to do. But there we know that the huge volumes were very, very bad for acoustically. They've got a 6 to 8 second reverberation time. So how did the people actually hear the wonderful polyphony that was being written by the Gabrielis, by Monteverdi, and people like that? Well, what we believe is that by the time you put in all the decoration, the hangings, the large audiences, we will be able to bring down the reverberation time so that not only the Doge himself, who had a wonderful experience because he would be in a closed volume, but everybody else could appreciate the genius of the polyphony.
Well, that's fantastic. I'm afraid we're going to have to leave it there, but that's Professor Malcolm Longer explaining how we can use acoustic modelling to recreate the sound of churches that have long since disappeared, or change their roofs, or change their dressings, and find out really what the experience would have been like.
Stripping down science. The Naked Scientists.
Now, in a twist to our usual kitchen science experiment, we're going to do something that certainly needs a kitchen, and it'll probably be done in most dining rooms across the country over Christmas. We're going to carve up a roast bird. But we have with us in the studio Dr. John Brackenbury from Cambridge University Vet School, and he's going to help to explain to us exactly what we see when we're looking at and carving up our roast birds, and point out a few interesting things we might find inside our Christmas turkey. Well, hello, John. Thank you so much for joining us.
Hi.
So we have with us, as well as John, a chicken, because it's a bit smaller and a bit cheaper than a turkey. And I don't know if anyone's going to want to go away and eat this after we've dissected it. So what are we looking at? What have we got in front of us right now, John?
Okay, well, we have on this plate a chicken, which has already been cooked. And instead of using a knife and fork, I'm going to be scientific. And I'm going to use some instruments. I've got a scalpel, I've got some scissors and forceps, and we're going to weigh in here. So I think I'll begin by kind of naming of parts, just to give the listeners an idea how this is laid out. So its rear end is facing towards me at the moment. It's on its back. That means then the first thing that we encounter right down here, right in front of my nose, as it were, is the parson's nose.
Now, that's its bottom, isn't it?
It is, yes.
That's fine. And we eat that, do we?
It's something of a delicacy, I guess. But it's important to the chicken because to any bird, actually, they carry their tail feathers on there.
So that's the beginning of it, where its tail
that's
is,
right.
basically.
That's the tail. And as you can imagine, a peacock's very proud of its parson's nose. All this stuff. Right, so that's right at the very end. Now, here we are, right in front of it. Now, at the front, we have the two wings. These are relatively scrawny, so I guess most people kind of ignore those. Then at the back, we have the drumsticks. In this case, they're crossed. And in fact, this chicken looks remarkably meditative. But anyway, I'm going to...
Sitting in the lotus position.
I'm going to uncross those legs to reveal the bit in the middle that most people are interested in, which is the breast muscle.
And that's huge, isn't it? I mean, compared to this, obviously, we've got the drumsticks, the legs, but there's an awful lot of breast meat there.
It's colossal. And, of course, that's why we eat chickens and other game birds. It's because of the breast muscle. Now, what I've done is, with my scalpel, I've made a cut right down the midline, because that will reveal interesting things. And with my fingers, I can then separate from the midline the outer breast muscle, because, in fact, there are two. The really big one on the outside is the obvious one, but in fact there is a smaller breast muscle deeper down there.
And do we eat that smaller one as well?
We eat them both. Yep. But from the point of view of the bird, these are very interesting muscles. They're actually equivalent to our pectoral muscles.
Oh, right, the pectorals, right.
Birds fly, and in fact the ancestors of this chicken actually flew a few thousand years ago, but they fly not using muscles in their arms. Their arms are actually very scrawny. But muscles, the breast muscles.
So these are both two sets of flying muscles, are
That's right. These are the muscles of flight.
Why do we need two sets rather than just a single set?
Very good question. Now, the one on the top, which is the one with the most meat, is the one that brings the wing down, the downstroke.
The downstroke,
That is the power stroke. Your listeners could do this by stretching out their arms in front of them, straight in front, clapping towards the middle as though there was an imaginary balloon, and bursting it.
So that would have to be quite hard to burst a balloon, wouldn't it?
It would. Well, that's what a bird does when it flies.
Oh, right. Okay.
And the thing that's creating that power, the downstroke we call it, is this great big breast muscle. Now, unfortunately, of course, chickens lost this ability many, many thousands of years ago. But as a result of domestication, we've built up the natural ability of this muscle to grow to such an extent, actually, that in a turkey, it could be nearly as much as half the entire body weight.
So we've selected for that.
We've selected it.
That's not a natural thing, but we wanted that meat, and we've, over generations, selected for bigger flight muscles.
Exactly.
Right.
Now, the result is a lovely tasting bird, but the muscle's completely useless for flying. It's just too big, it's lost all its natural strength, and it's only good for eating. Now, the other one we mentioned, the deeper one, that's used for the upstroke. So that does the opposite movement. When a bird wants to bring its wings back up after the downstroke, it uses that smaller one. Right. So these are two pectoral muscles, and they're used in flying. Now, the other thing that we've exposed by separating the meat along the midline, it's very easy to do, several things. First of all, right in the midline, and if your Christmas listeners do this, they'll see a ridge of bone. Actually, in this chicken, it's a ridge of cartilage. It should be bone.
Oh, right.
But nearly all chickens are slaughtered so early in their life.
I see. So it's because it's young, it hasn't become bone yet.
It's not had time to turn into bone, so it's just gristle. So that's one thing. And in
fact,
fact,
is that where the muscle's attached to? Is that why it's there?
That's where they're attached to, and that's why it is so deep. It's actually about 2 centimetres deep, because this great big breast muscle is attaching to it. Anyway, that's one of the things we can see in the midline. Now, if we move towards the front, towards the neck of the chicken, we see something else, which everybody will know. That is the wishbone.
Right.
And
that V-shaped...
That V-shaped
bone
right at the front. In fact, technically, this is called the little fork, or furcula. And it is a fork. It's shaped like a fork. Anyway, that's one of 2 sets of collarbones that birds have.
Oh, so this is the bird's collarbone?
That's right.
Right.
But that's the little collarbone, and actually it doesn't do much. But deep down, under that second layer of muscle that I mentioned earlier, is a second set of collarbones. These are much stronger, and they're essential for flight.
Is there 2 collarbones because there's 2 sets of muscles?
There are 2 collarbones because the wishbone itself is a bit of an apology. It won't really do the job which any flying bird needs to do, which is to stop its shoulders crunching towards its breast when it makes a powerful beat. And the function of that deeper collarbone is to stop that happening.
So would we get an even better wish if we broke the inner collarbone?
You would, but it takes a bit of getting to. And I think by then you'd be so tempted to eat this thing that I think you'll have forgotten all about the functional aspects.
Excellent. Well, we're certainly getting into the grips of this chicken. If we were looking at a turkey, would it be very different, or are they structurally very similar once you get inside them? Or a goose, say, or a duck? Even?
Yeah, there are differences, mainly on account of size. Now, the turkey is going to be very similar to the chicken, whereas the goose is going to be quite different.
Right.
The turkey and the chicken have white meat. It has a distinctive taste because it's full of something called glycogen.
And that's what makes... So we have white and we have red meat, is that right?
That's right.
Yes, and those are... Why are those different?
They're different. As I say, the white meat has glycogen, and that tends to be used when a muscle beats very quickly, but exhausts very quickly as well.
So sort of very, very fast.
Very fast.
Right.
Powerful movements, but it soon tires because its energy reserves are very limited. Whereas red meat, and actually in the chicken we find the red meat mainly in the legs, because the legs do work. Chickens run. And the red meat has a different set of enzymes, different set of chemicals.
Excellent. Well, the mess we have in front of us might be good for some soup perhaps later. It's definitely given us a fantastic introduction to the chicken. Thank you very much to Dr. John Brackenbury from Cambridge University Vet School for carving up a chicken for us.
This is The Naked Scientists. I'm Ben Valsler. We also have Helen Scales and Dave Ansell with us. And we've had a few of your questions that we're going to get to in just a sec. But first, we had a comment from Douglas Toltzman, who said that last week we had a question which was, is it really true that you should feed a cold and starve a fever? Now, he's written in to say that regarding that saying, as he understands it, it's been dangerously abbreviated over time. The verbose version of the saying, as he puts it, that reflects the original meaning, might go something like, you should feed a person who is suffering with a cold in order to mitigate them developing a fever. So thank you ever so much for that, Douglas. That's not something I know. I've always heard it as feed a cold, starve a fever.
Absolutely, yes. We've got to get it right, though, don't we?
We should, of course. Now, we've had a few more questions, and this is one that seems very relevant when we have a roast chicken on the table in front of us. And that's, why is unhealthy food so tasty? Gert asks us, why is it that fast food tastes great, but not vegetables? And why does deep-fried food taste really, really tasty, but it's not actually good for your body? Now, Helen, you clearly have something to say about this.
I have something to protest about this. Vegetables can be very tasty. I in fact made a very nice nut roast this weekend. So I disagree on that point, but I'm afraid, I'm nasty feeling that not everyone agrees with me.
I think you're right. I certainly agree with you. I think especially fresh vegetables, when they've still got all of their lovely taste straight from the garden, are really tasty. But I think the deep fried, the fast food, the high calorie stuff, I think that's probably a bit of an evolutionary throwback. I think our body rewards us for taking in lots of calories. And so when we do this, it used to be essential to find food, and so we'd get a molecular reward in our brain that says, well done, you've found some good, rich food, that will keep us going throughout the winter. And so we get that sort of pleasure sensation. Now, food isn't really a pressure like that, and we still get this reward. So when we eat something that's very full in calories, this brain mechanism kicks off, and we think that we've really enjoyed it. He also asked, and this is a very interesting one, Helen, again, I'm not sure if you might have something to say about this. He said, is there any deep-fried food that's better than others? Now, I'm not sure how you serve your vegetables, but...
Tempura vegetables are quite nice, aren't they? And that's a form of deep frying. I mean, I'm sure a deep fried piece of broccoli is slightly less good for you than a piece of nice, fresh, unfried, slightly steamed broccoli. But you still, if you haven't overcooked it, you're still getting lots of the nutrients and the vitamins that are so important in vegetables. If you do that kind of style of cooking, so that's not too bad, I should say. That
was exactly what I thought, because with tempura food, the food is still very fresh and it's fried only for a very short time. In fact, you're supposed to use ice cold batter, and apparently that's why it's so fluffy and tasty. But the food isn't overcooked, and I suspect actually that boiling carrots for 10 minutes would probably get rid of more of the nutrients than deep frying them for 1 minute.
Oh yeah, I quite agree actually, yes. I think if school dinners could be more tempura vegetables instead of carrots boiled to death, then that would be a good thing, I think.
We've had another question from Jeremy Kroll. Now, I think really he's joking with us here, but I think there's a couple of valid points. He's asked us, why are scientists promoting a religious holiday?
I think it is very strange that we're promoting a ancient Roman holiday of Saturnalia, when everyone used to get drunk because it was the winter solstice and eat lots, apart from anything else, because all the animals would have to be slaughtered because they wouldn't survive the winter, especially in northern latitudes. I mean, it's basically a holiday which every religion which we know of has used.
I actually don't think it is that strange. In fact, I think maybe it harks back to a really important part of human social evolution, which is wanting to belong to a tribe, and that we want to belong. We want to feel we're part of a group. Because that was beneficial, and it meant we could do better things in a group compared to just on our own. And I think that's maybe, I don't know. I think it harks back to a bit of that. Why? Because we all join in together and we're celebrating the same thing, and you know, whether it came from a different religion or not, then why not?
And of course, it's kind of depressing this time of year in northern latitudes, so you want something to cheer you up, whatever religion you have.
Exactly.
And Christmas is a very good excuse, of course. Well, now it's time to go for our question of the week, but unfortunately Diana O'Carroll has been snowed in this week, and so she sent us this recording from her homemade igloo.
This week I've been eating lots and lots of chocolate to see if it's poisonous.
Hello, this is Alvin Raj from Cambridge, Massachusetts. Why is chocolate poisonous for dogs?
It seems like the ultimate torture, something so extraordinarily delicious, tasty, flavoursome, a food of the gods, and yet it's poisonous.
I'm Sorrel Langley-Hobbs, University Surgeon at the Queen's Veterinary School Hospital, University of Cambridge. Yes, chocolate unfortunately is toxic to dogs, and the reason it is because it contains a compound called theobromine. Theobromine and caffeine are both present in chocolate, but theobromine is the problem, and they're both methyl xanthines. In dogs, theobromine is very long-lasting, so it's got a very long half-life of about 18 hours, whereas in people, half-life is only 2 or 3 hours, and people readily absorb the theobromine. I think it's just the fact that every species has different metabolism. We see differences between dogs and cats with certain drugs. So, for example, you shouldn't give a cat paracetamol, whereas dogs can tolerate paracetamol. So it's just a species difference, probably different enzymes that are present in the system. So how much theobromine is toxic, you might ask yourself. So if a dog eats a couple of M&Ms, that's not going to cause any problem. The toxic levels vary from 20 milligrams per kilogram of theobromine to about 150 milligrams per kilogram of theobromine. So what does that mean in reality? Well, putting it into a typical scenario, if you've got a Labrador and that ate a 200-gram bar of dark chocolate, that potentially is enough to kill your dog. So it's actually not very much. And the big problem at this time of year is someone giving you a box of chocolates, wrapped up, you put it under the Christmas tree, and the dog eats the box of chocolates. And if that happens, you certainly should call your vet as soon as possible.
Theobromine is the chemical culprit responsible for poisoning dogs. Their digestive enzymes simply can't break the chemical down fast enough, and if they have enough of it, it's toxic. You can get alternatives for your dogs, though, which are made from carob pods rather than cocoa. On the forum, Majida Scientia mentioned that the body weight of the animal can play a part. Board chemist said that selective pressure for digesting plant-based chemicals, like theobromine, had never been placed on dogs, as their ancestors would have been predominantly meat-eaters. And it seems we all might have to make some adjustment to our environment for the next question of the week.
My name is Jenny Boyd. I live in Edmond, West Virginia, United States. My question is, how is carbon output, carbon emissions measured for various countries, and how accurate are those measurements?
Do they just guess? How accurate are CO2 measurements? Email answers to us with the address chris@thenakedscientist.com, or use the forum to talk about it with other listeners, and that's at thenakedscientist.com/forum.
That was Diana O'Carroll with our question of the week, recorded in the middle of a blizzard, by the sounds of things. This question really caught your attention on the forum, so if you'd like to see the rest of the discussion, go to thenakedscientist.com/forum, where you can also put your ideas forward for this week's question. That's all we have for this week. We're going to have a couple of weeks off, but we'll be back in January to explore the science of hearing. We'll be looking at the genes that let you listen to radio, as well as investigating where you sometimes hear something that isn't really there. Now, many thanks to Ian Mackay, Malcolm Longo and John Brackenbury for joining us this week, and we've got to say thanks to everybody who's joined us throughout the year. Thanks also to Chris and Kat, who aren't with us but should have a wonderful Christmas, and thanks to our production team, Mira Santhalingam, Diana O'Carroll and Tom Simpkins. Thanks to all of you at home for listening. Have a great Christmas, and we'll be back with you soon.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.